All right, so today we are going to do the management zones. And I think at least for me, it's like one of the most exciting parts of this because it's really where we bring it all together and connect things and try to understand if how many zones this field would require and what are the main drivers of those zones. So I'm just showing you here again my main project or my main folder for the course. And we're going to just like you can go into your own project and then launch the RStudio project icon right there. So it takes us to our analysis or to our scripts here in our environment. And so I sent you guys an email last night asking for you to download from GitHub pretty much the code for today, which is the zone partial. So if you have done that and moved that into your folder, you should be seeing it in your code folder. So you can go ahead and click on that to launch that on the left side here. And you can also go ahead and minimize the console by clicking on this button here because we're not going to be using that. And I also asked you to download, from GitHub and also copy and paste into your data folder 3 data sets. And I want to quickly tell you why. Even though we have already created those data sets, but I want to tell you quickly something that I ran into and how I solved the issue and how this was impacting those data sets. If you remember, every time that we were joining spatial data sets and exporting them to file, we were using, I briefly told you about this, but I was using the stjoin function, which is supposed to be used when you're joining spatial objects. But the default behavior of that function was not giving me what I wanted. So when we do that spatial join, we should still have like 4,032 rows. And when I was using stjoin, it was giving me like 33,000 as the result, which is definitely not right. So I decided to take a step back and not use stjoin and instead use left join, which is normally what you would use for data frames that are not geospatial. And it worked, it did the job. But then when I was developing the script for today, I noticed that some of the layers were not looking like the way they should when I was plotting them. And I realized that the issue is that, so the way that I was showing you guys to use left join and using that ID to do the join works nicely if all layers have the same number of rows. So it was working nicely until a given point. The moment that didn't work for us is when we brought in slope and aspect. And the reason for that is because slope and aspect cannot be calculated on the boundary pixels because it needs a neighborhood around the center pixel to calculate slope and aspect. And so every time we calculate slope and aspect, we lose the boundary pixels because they don't have all pixels surrounding it. And when that happens, so the slope and aspect layers had less data points, had about 300 less data points than the other layers. And when we did the ID didn't really know exactly which ones were missing. It just added 1 through the total number of observations. And when we joined them, things were looking weird. So I just wanted to tell you that the way that I showed you in class previously, actually, it worked nicely until we ran into the issue of bringing layers with less number of observations. And then that broke pretty much the quality of those maps. So my workaround for it was to go back and read more on the documentation of stjoin, which is the function that we should have been using, or that I tried using the first time, but then didn't work the way I wanted. And I noticed that to make that function, the stjoin function, to work the way that it should have, I had to change one of the arguments so that there is an argument called join that the default behavior is st intersects, and I should have changed that to st equals. So when I went back and did that, now all the layers were doing the spatial join using stjoin. So not using the ID anymore, but using the spatial extent. and it was doing the proper way. So I just wanted to bring this to your attention because of two reasons. So one is the code that I showed you to do the spatial join using the ID and using left join function. Again, it works if all of them have the same number of observations, but I decided to go back and change all the scripts that we had used that approach. I went back and changed on the completed versions of those scripts to actually have the use of st join and changing this argument to st equals. So it does what we wanted. So I changed those completed scripts, and those scripts include the terrain, soil ECA, and yield stability scripts. And I have already updated those scripts with the new code and sent to GitHub as well. So you have that for your reference. You know, if you do this in the future, again, you can use the completed versions to really see how it should have been done. And it's just a change of that specific chunk where we, instead of using left join, I was using st join with the proper configuration of the arguments. And also I went ahead and so on my side, I changed the script, the completed scripts, and I also reran them and recreated the files that we were exporting. So that's why I asked you to actually download from GitHub those 3 GeoJSON files and copy and paste into your data folder. That was the main reason, because they are going to be different than the ones that we had before. And also something else I found out when I was preparing this class is that write SF can be tricky. So if you are using write SF on a given object and saving on a given file name for the first time, it does exactly what you wanted, right? It would create this layer with 4,032 observations. However, if you for some reason want to make some changes in the code and re-export that layer, so the same object, same file name using write SF, write SF does not overwrite by default, it appends. Meaning that if you already have that file created previously from a previous use of write SF and you use it again, it will basically double the number of rows of that saved file, which is not what we want, right? So also to avoid that happening, we have to include this argument here on the write SF function, that is delete dsn equals true. So this deletes that file that's already been saved and overwrites pretty much on the same name, but with the updated object. So I know this is like a lot of talk that, you know, it can be a little bit confusing, but I still wanted to bring this up to your attention because I made these changes in the code that we used on the completed versions of the code that we used to reflect these changes. So if anytime you need a reference and you go back to the completed versions, it's going to be correct. But I just wanted to tell you that I found these issues out when I was developing the partial or the zone exercise. And I just wanted to make you aware of that. Any questions related to that before we get into today's exercise? Okay, I don't see anything. So I'm going to keep going or get started actually with today's exercise. Okay, so today what we're going to be doing is importing all the process data that we had, which was like the clean and interpolated versions of the data that we've been building up until this point. Then we're going to do a spatial join to bring all of them into a same data set. So the terrain variables, the soil EC variables, and later on the spatial temporal variability of yield variables as well, all in one data frame. And then once we have it all together, we can do a clustering analysis. Today, I'm going to be showing you analysis called k-means, and we're going to get more into that. I'm going to explain and walk you through what it means, what it does, so you really understand what's going on behind the scenes. But that's a very common clustering algorithm to be used for like management zone creation. Many papers use this. It's a very popular one, perhaps one of the most popular clustering algorithms out there. And then after we do our clusters, and I mean, I'm saying cluster and zone, kind of using those terms interchangeably, because cluster is the name that, you know, is more related to the analysis, but zone is the same thing, but is more related to the application and precision act. So just keep that in mind. So then we're going to assess how all of our variables are impacting these clusters, and then we're going to validate those clusters with yield spatial temporal stability areas. Okay, so beginning with the code here, I am going to use three packages that at least we haven't used in this class yet, which are the Facto Extra, NBclust, and ggpubr. So I left you the commented off install packages there. If you don't have these packages installed, which again we haven't used in this class, just uncomment and run each one of those lines one by one. And once they install, you can just comment them off again because we only install once. And while you do that, I just want to tell you that I have already included those three packages on the library part of it. So once you have installed, we can just go ahead and load that. I'm just going to run this chunk. And it should not have given you any issues installing, but if you had issues, this is the time to speak up. All right, so I don't hear anything. Let's keep moving. So first step here, as we mentioned already, is going to be to bring back into our environment the objects that we have already cleaned and processed, interpolated, and exported. So let's begin with the terrain one. I left you the code there, so we don't have to do much. Just run it. And something I want you to notice here is, well, as always, a few things that we should notice. So one is the proper number of rows, right? So we know that our grid had 4,032 cells. So this is what we should have as far as observations for all these layers. If we come back to the first pane here, just want to show you that it is a polygon. It is in the proper CRS. So this is what we want to have it. Always like to check that, because if it's not, then we have to transform it. And then if we come back to the data set, now I want you to notice how on the slope and aspect columns, there are some NAs here, and also on the flow direction. And so, and the hill shade, actually all of the terrain ones that are using slope and aspect have NAs. And that's just because of what I was telling you in relation to those pixels in the boundary of the field don't have neighbors all around. And so that's when the NAs are created. Okay, so let's bring in our soil electroconductivity data, which again, I left you the code. And here, again, we notice that it has 4,032 rows, so that's right. We check here, that is the proper CRS, it is. Awesome. I also want to bring in the boundary, and I just want to show you quickly here, if I just comment off this pipe, and I just read that first line of code there and print it, the boundary, maybe it's when we saved it, but the boundary comes in as WGS84. So that's why this is the only layer that I'm actually going the little extra mile and using the ST transform to bring it into UTM in 8083. So if you just run like with the pipe uncommented and letting it go through and you print it, you see that it should be in the proper CRS now. Okay, so the first thing that you're going to be working with me here on coding is to actually join all these data sets together. And I will be showing you here the proper way that we should have done from the beginning, and the way that I went back and changed on the previous scripts as well. So we can just go ahead and add the assign symbol. We're going to start with the terrain _v. So that's going to be our first layer that we're going to provide here. You can add a pipe, hit return, and then we're going to use the function stjoin. Again, notice as before we were using left join. Now we're not doing that. We're using stjoin. So stjoin does also a join, but it's based on the geographical information of the layers. So we're going to basically join terrain with ECA _v. I just want to run this as is, so you can see why it's not giving me what I wanted with the default argument. So if I just do the join that way, it returns me a data frame, a geospatial data frame with 35,000 observations, which is clearly not right. It's doing something wrong behind the scenes, And this is why I decided to not use this function initially. But then again, ran into the issues, came back and actually found a workaround. So the workaround to not have this erroneous join here is to change a couple of arguments. So we're going to add a comma. I want to hit return just to give me more space. And there's an argument called join. So the default here is st intersects. We're going to change that to st underscore equals. And it doesn't have to have the open and close parentheses, just st underscore equals is fine. You can add a comma, and then there's another argument called left to say that is a left join. We're going to say true. So if we run this code now, our join should give us the 4,032 rows. And now we can notice, I'm just going to go like right here so we can see. So we have elevation, slope, aspect, flow direction, hill shade, and geometry all coming from terrain. But if we keep going, we find the ECA 30 and 90, which are coming from the ECAV. So now this spatial join worked as it should have. And this is basically the code that I changed everywhere we use left join on previous codes. Now I changed to this st join, making sure to change these two arguments as well. Okay. Oh, sure. Yeah. Mm-hmm.
Dr. Bastos, can you hear me?
Yes. Mm-hmm.
Yeah, I want to ask that our ECAV file, since does not have an ID column, so does the st join over here is using the geometry column to join the both the files?
Right. So now we are not using the ID at all, right? We're using the spatial extent and size of those layers. And that is, again, one of the reasons why we wanted to use a grid and bring all the layers to a common grid size and extent, because now everything is matching, right? And if we can just use this st equals to really extract those, or not extract, but join those layers by that same grid configuration. Yeah. Okay, so I want you to come to the next chunk here where we're doing some exploratory data analysis. And I just want to print that summary. And I want to do this basically to show you that. So we notice here that some columns, so all of them, almost all of them are numeric, right? Except for flow direction and geometry. So because they are numeric, the summary function gives us the statistical summary, right? And you notice how for some columns we don't have an NAs row, and for some others we do. And I just wanted to make the point here that the ones that have NAs are slope and aspect, and then hill shade, and that's it. And I guess flow direction also has some NAs, but is not showing here. But the point I want to make is, again, slope and aspect calculation at the border of the grid give NAs because they don't have enough neighbors to do the calculation. That's why we have some NAs in those columns, and hill shade because hill shade depends on slope and aspect as well. I just wanted to make that clear. And you don't see any more NAs in any of the other columns, as we would expect to not have NAs in those columns. All right, so let's get into a little bit of theory of k-means. And let me just, I want to ask everyone here. So I personally learned about k-means during my PhD. So I just want to gauge a little bit if anyone here has heard of it, has seen this, read about it, used it perhaps in their research. Anyone familiar with k-means or clustering algorithms in general? Okay, I don't think anyone is. So awesome. I included some information here that should give you a good understanding. And please, if I'm going too fast here, if I am not being clear, stop me, ask questions. My goal is for you to understand this and not just be a black box. Okay. So a couple things here, and I added a lot of text to the script, mostly for you to read later if you want to. And I will be talking about some of these points, but I'm not going to be reading them incomplete just here in class. But so k-means, it is an unsupervised algorithm. And if you have never heard of this, It basically means that you're not telling it what to look for. You're not giving it a label to then try to predict that label. So, and this is going to make more sense when we get into some of the graphs that I have here to explain to you. But just keep that in mind. It is unsupervised clustering algorithm, and it's going to partition the entire data sets. We're going to give it our data, and we're going to say, find groups. That's it. Just going to say then how many groups we think there is in this data and tell k-means to find those groupings for us. And one of the things is that k-means is going to find how many groups you tell it to find. So if we tell it to find 2 groups, it will do that. If we tell it to find 100 groups, it will do that. So it is up to us to give a sensitive value of k, or in other words, of groups for k-means to identify in our data. Okay, so I want to go ahead and run that chunk. It just has a figure that I want to show you. So this is a very simple example of a data set where we're going to use k-means to create groups here. So it doesn't really matter what x and y is. This is not our data, but it's just a data set that has 2 columns, x and y. And those data points are plotted here for us to see. So for you, for us as humans, if we look at this, how many groups do you think there is in this data set?
3.
3? I agree. Visually assessing, it looks like there are 3 groups, right? I agree with that. Okay. So that would be a good guess, right? So if we look at this and we say, okay, it looks like there are 3 groups, let's give that number for k-means and see how it does. However, there's one, so this example is a very simplistic example where we only have 2 columns, so 2 variables that we're using to cluster. You could think of this, I mean, this is not elevation and slope, but let's say that we had elevation and slope, and those were the only 2 columns we had, and it was clear as water, I guess, and not as mud, that there are 3 groups in this data. However, in our case, we actually have maybe like 7 variables that we're going to give to k-means. And our brain, our human brain, it's really difficult for us to make sense once you have multiple variables. So, okay, let me take one step back here. So every time in mathematics that we talk about a new variable, it's also adding a new dimension to that data set, right? So here we have 2 variables. We're looking at this plot in 2D, right? 2 dimensions being shown here. Every time you're adding a new variable, you're also adding a new dimension, mathematically speaking. And our brains have a limited capacity to interpret visually when dimensions go above 4. So maybe we can add a 3rd dimension and make it like X, Y, Z, and maybe change the color according to a 4th variable and add that 4th dimension with color. But that's about it. Our brain has a hard time interpreting more than 4 dimensions, which can make it difficult for us to visually assess, okay, this has 3 groups. I mean, what if you have 100 variables? How are you going to even plot them to see how many groups you have? It's kind of difficult. So we have to have a way of checking how many groups there is in a data that has multiple variables that we cannot just visually inspect. Okay, let's just come back here to this example here. So how would k-means work in this simple example? So the way that k-means works is, so in this case here, we're telling it that we want it to look for 3 groups, okay? So what k-means does is it goes into your data set and it selects 3, in this case 3, because we're telling it 3 groups, so 3 random samples from your data set and assigns those as the center of the clusters that is going to look for. So in this case here, the step 1, we can see that as that observation being one center, this observation being a second, and this being the third. And then once it does that, it calculates the distances of each data point to each of these 3 centers, and it assigns a membership to each observation according to the shortest distance of that observation to one of the cluster centers. So I know this can be a little bit confusing, so let's just walk through here. So we randomly selected those 3 observations, right? And if you see everything that's green here It's green because though all those green data points are closer to this center than to any other center. And the same happens for the other colors, so the purple and the red here. Okay, so this would be the first step that K-means does. Selects 3 randoms, or in this case, again, 3 because we're telling it to do 3 groups. So 3 random samples, calculates distances of all points to all 3 centers, and assigns a membership to each observation based on what center is the closest to that observation using a distance metric. Okay. Is it, let me see your faces on Zoom. Is it making sense?
Yeah, it does.
Awesome. All right. So so now how does K-means, because I mean, these 3 random samples are random. They could happen like all clustered in one side of the data set. And then how does K-means really navigates and learns where the centers, the true centers of the data should be. So what it does now is once it assigns a membership on this first round, it basically uses all data points within those clusters that are created now and calculates the center of those clusters at this step. So what's going to happen then is this cluster is not going to be centered here anymore. The center is going to be somewhere here. And the purple one's going to be around here. And the green one's going to be around here. So at each step, it moves that center a little bit, recalculates all distances, reassigns membership based on distance, and keeps evolving that way in iterations until the center means don't change anymore, meaning that it has converged. It has found the true centers of the clusters of this data. Okay. So I want to show you a GIF that shows in 12 steps what's going on. It is going to go a little bit fast. So we're going to watch it a couple of times perhaps, but it's doing that. So we see the step number up here and pay attention on the axis and how they're changing. So raw data, selects 3 random samples, starts shifting those centers based on recalculating distances, setting the center again as the mean of those new distances or new observations that now belong to that cluster, and just in different iterations. In this case, took 12 steps. So 12 iterations of starting with random samples, calculate distances, assign membership, using all those members now, calculate the new center of that cluster by taking the average of all of those observations, and then just updating as it goes. So this is basically how K-means navigates your data and find the 3 clusters. And it's really interesting to note because we do see that in the first iteration, these 2 clusters were actually one. They were the green, all those 2 groups of data points belong to one cluster, right? The green cluster. And as K-means navigated and started updating the cluster means on different iterations, we see that it was able to find the 3 actual centers of the clusters of this data by doing that step by step and updating the center of the clusters. Okay. I know this can be a lot, it can be confusing. If you did not understand, please let me know. I'll try a different approach. And the thing is, again, this is a very simple case, right? This isn't in the data set that it's using 2 variables. We're going to use 7 perhaps. So how the thing is also to think about here visually, we could see that there were 3 clusters and we just let K-means find them. What, again, if you have so many variables, you cannot plot them. So you don't have a good visual guess to say, oh, there are 3 clusters here. There could be 2, there could be 50. How do you know, right? So that's what we're gonna look a little bit next. Okay, some of the properties of K-means. So K-means, it is a clustering algorithm, as we've been talking about it. And every time you hear this word clustering algorithm, it is what is used to create management zones, because we are clustering a whole bunch of observations into groups, right? So that is the overall type of algorithm that is used for management zone creation. It is unsupervised, and the reason why is there is no outcome, or so outcome, response variable, and y are all describing the same thing. So there is no outcome in the formula. You're not saying like yield equals all these variables. We're saying there's no y in that formula. It's just a whole bunch of x's that is trying to combine all those x's together into groups. And that's what makes it unsupervised. And along with that, it only takes predictors. Again, only take X columns. It does not have a Y. It's not trying to explain something. It's just trying to combine all the X's together. And one property that could be seen as a downside of k-means is that it only works with numerical variables. So categorical variables do not work. K-means does not handle those, which means that we're going to have to say goodbye to flow direction on this analysis, because flow direction, even though it's at 1, 2, 4, but we've seen how those numbers don't have a numerical meaning. They have just a direction meaning into that matrix. So we're not going to be able to use flow direction for zone creation here. Okay, I want to show you something else before we start really going through some of our data here. So k-means is very useful if your clusters of data are circular, are round like this, right? We do see that they have this oval circular shape. K-means does great in those situations. However, k-means does not do as well if you have odd shapes or outliers in your data. And I want to show you this figure here is from a paper that I think is really amazing. I'm going to pop this out so we can see more enlarged. So this paper was, they made up data with different shapes. And you can see like each one of the shapes is a row here. And then each column is a clustering algorithm. Again, k-means is one clustering algorithm. There are many out there, even more than I'm showing here. So each column is a different clustering algorithm, okay? And then they're basically showing the performance of each one of these algorithms in finding the proper clusters, right? So for example, let's just look at this first data set where we have the two circular shapes. And this is a good, even though this paper is not ag related at all, but if you think of it, where in agriculture, in precision agriculture, could we see this type of, I mean, if you think that X and Y are spatial coordinates, which they're not, but where would you see this type of shape in precision agriculture applications?
Irrigation.
Yes, irrigation, right? So let's say that you have a data set, or you're trying to make a model that will predict, will create zones of whether or not your nozzle is clogged or not. And the shape of that response is circular, because if a nozzle is clogged, you're not irrigating, so your plants are not growing as well in that part of it, but they're growing well elsewhere. So this could be something that would be, that you could look for clusters where it would be well watered or not well watered, or clogged nozzle, non-clogged nozzle would be this. So you see that what k-means does is it does not realize that you have that continuity on a circular shape. And it tries to split those two, because the groups there would be smaller circle, larger circle. K-means is split right through them, and it does not do a good job, right? However, we see that k-means does a good job here, for example, where we have circular shapes. And this first column here is k-means, just so if I hadn't mentioned that. So if you have this type of data, of this type of shape of data, then maybe it would be better to use a spectral clustering, or maybe dbScan or others here that would better fit that type of data, right? So I just wanted to show you this to make the point that yes, k-means is good and it's very popular and used by a lot of people, but we have to be cautious because it's not the silver bullet that, we have to keep that in mind. It has some shortcomings. Okay. And again, I guess we talked already about the issue of this. Again, is a very simple data set with only 2 dimensions. What if you have 10 dimensions? How do you visualize that? It is difficult. It's almost impossible, really, to just do a plot where you include so many variables. And so that is what in statistics is called the curse of the dimensionality. You have so many dimensions in your data. Great, you have big data, right? Awesome. But then there are also downsides of that, because you start increasing complexity to a level that you have to know certain tools to handle that. Okay, so let's actually do start working with our data here. And two things that k-means does not handle, and we talked a little bit about some of them. So one is k-means does not handle NAs. If you have even one NA cell in your data set, k-means is not going to work. It's going to throw you an error. And also, as we already mentioned, k-means does not handle, well, it only handles numerical columns. So if we have categorical variables like fold direction is, and in our case, our data set has a geometry column, which makes no sense to include in a clustering algorithm, really, not in that way at least. So we have to do some cleaning in our data before being able to feed that into k-means. So let's do that. I left you here the name of the argument that I want to keep. So all v is the version that we have now, and I'm adding that n there just to say that is only numerical, but we're also going to remove NAs. So you can just go ahead, start with our object that is all underscore v. We add a pipe, and we're going to do a drop underscore NA. So this column drop NA basically is going to look at all of your columns, and for any of those columns, if you have even a single NA value, it's going to drop that entire row. And it's going to do that for all columns. So if we just run at this point and just print all VN, now we're down from 4,032 data rows. Now we're down to 3,700 approximately, because we have all those NAs in slope, aspect, and hillshade. Okay, so we removed NAs. So this data does not have any NA cell. We also have to remove the categorical variables and the geometry. So we add a pipe. We're going to use dplyr select for that. And we just say minus flow dir and minus geometry. Okay, so if we do that and we print it, now we remove two columns, and if you just browse here, you're not going to find flow direction and geometry in this all VN data set. Okay, so our data is ready to go with k-means. So let's just do a first run of k-means, and I am proposing here that we tell it that we want 4 groups, so 4 zones, we can think of that in our data set. So let's just start here. I want to save our k-means results to this object called mod underscore km. So we can just use the assign symbol, and the function is called k-means. So the first argument we give it is the data set. And notice how we're given the entire data set, which is basically telling k-means to use all those columns as the axis of the formula, as the predictors of this formula. We can add a comma, and it has an argument called centers. So centers would be the k number, would be how many groups you wanted to look for in your data. We're going to start with 4 just to try it out. And then also another argument here is n start. I just want to show you that. So n start, I want to have it set to 10, and I'm telling you what n start is following here. So because k-means has a random component, which is that first step of selecting the initial centers, that it randomly selects observations in your data, we have to run it multiple times just in case it happens that you end up if you just run k-means once and you end up your random samples are all together in one side of your data and it has a hard time finding the actual centers throughout. This n start here is basically telling k-means to run 10 times. So if in one of those runs it ends up having a difficult time to find the centers, it has another 9 rows to compensate for that and give you a more realistic result. So that's what n start is doing. Okay, so we can just run this, and it ran pretty quickly. I just want to print this object and kind of show you what's going on here. there's a lot of stuff here, but one of the things to notice. So because we asked for k-means to find four groups, it did find 4 groups. And here is giving us the center of those groups for each one of the variables that we gave to k-means to even create the groups. So it's saying here that for cluster number 1, and it has an elevation average of 50.5 meters and so on, each one of the variables. You can see that. So each row is a cluster that we asked it to create. And then it also has, it gives you the membership for each one of the observations. So this would be the membership for each one of our 3,700 observations that is going to range from values of 1 through 4, because again, we asked for 4 groups. So it created 4 groups for us. And then it also has this information here. So it takes the between sum of the squares and divides by the total sum of the squares. I'm not going to get too much to the details of what sum of the squares mean, because it's, depending on your stats background, this could get a little bit more complicated to understand. But what I wanted to get from this is that the higher this value is, the higher the better, in the sense that you are explaining more variability with the clusters. However, there's a trade-off, and we're going to talk about that in a second. Okay, so when we asked k-means to give us 4 clusters, we got this ratio here, the between by the total sum of the squares, to be 63.7. I want you to come back to the code here, and let's just try, let's see what I had here. Let's try a k of 3, so centers of 3 groups, okay? Let's just run that and print the result again. And let's just check our value here. So now, if you can just copy in that and paste here, because I want to look at that number. So when we had k equals 3, now our ratio decreased, right? So before, with 4 groups, we had a 64% explained. Now we only have 57% explained with our groups. Okay, interesting. Now, what happens if we increase? So we were at 4, we decreased to 3. Now let's increase to 10 and see what happens. Okay, so come back to your code, change centers to 10, and let's run this and print it. So now our ratio is 80.5%. I just want to copy that and paste down here so we can look at those numbers together. Okay, so you can see here that as we increase k, the proportion of variability that we're explaining is increasing, which is good, right? We want to explain variability. So does that mean that we should have 10 zones for our data? Not really. And let me tell you why. So there is a trade-off here, because every time you add a new group to our data, you will always increase how much variability you're explaining. However, the first ones the first groups that are created are really the ones explaining the most variability. And there is a sweet spot that we have to find between how much variability we're explaining and how many groups we have in the end. Because, if we bring back to a precision agriculture application here, if a farmer's field is so variable that that farmer would be better off having 10 zones to manage, then great, then use 10 zones. However, if that farmer's field is not as variable and only has 2 to 3 zones, and you give that producer 10 zones to manage, it's just extra work that farmer is not going to be getting the benefits from, because it would have been just as well with only 2 to 3 and you gave that person 10, even though 10 explains more variability than only 2 or 3. But there is a trade-off, right, between complexity and how much variability we're explaining. And we need to find that sweet spot. So how do we find that sweet spot? How do we know the optimum number of groups for any given data set? That's what we're going to be talking next, because it's a really important aspect. And well, I guess you can just leave the code, because we're not going to use this object anymore. So it's okay if you leave it 10, or if you want to play with this and add 100 or 0, whatever. It's really just for us to play and see what is changing. Okay, so how do we find the proper value of k for a given data set? So there are multiple different metrics that we can use to do this. And all of them, what they do is basically they run k-means for, let's say, they run k-means for one group, and then for two, and then for three, and all the way to a maximum. I'm restraining our example here for k-means to start with only one cluster and going all the way to 10 clusters. So that's our limits here. And it's going to give us some metrics related to how much variability is being explained and how compact those clusters really are in the end. And we want to understand this trade-off. So the first one that we're going to explore here is the within sum of the squares method. I want you to come here to this chunk, and we're going to use a function called fvis with z underscore nbclust. So this function is coming from one of the packages that we just installed above. I think is the nbclust perhaps. So if you're not seeing this function, it's probably because you either didn't install or didn't load the package. Let me know if you have any issues. If you're able to auto-complete the function, then you have it. So the first argument we're going to give it is our data set. So it is all underscore v underscore n. And then I want to add a comma and change a couple arguments. So it has an argument called method. I want to say method equals open and close quotation marks WSS for within sum of the squares. Add a comma. It has another argument called k.max, which is when you tell it how many, what number of k maximum you want the algorithm to evaluate. I want to say 10. So a 10 maximum of 10 zones I want it to evaluate. And then it has another argument called fun, like FUN right there. So fun cluster, which is what function we want this, or what algorithm we want this to use to determine for us. So we say fun cluster equals k-means, and k-means does not need to be within quotation marks. So if we just run this, maybe it's going to take a little moment to go through, or maybe a longer moment to go through actually. I mean, at least for me, this is how it worked. So maybe it's still running on your side, but you can just look over on mine and see the output I got. So what happens here is on the x-axis, we have the number of clusters. So it's starting with 1 all the way through 10. And then on the y-axis, we have the total within sum of square. So this is basically telling us how much variability is being explained by adding another cluster to the analysis or another zone. Normally, we want to select the number of k where we have the elbow break, where we have like a corner here. For this specific data set, it's not as clear. I've ran k-means for some other data sets that you really see like a very broken elbow shape. This is more gradual, which makes it a little bit more complicated. But you see that going from 1 to 2 clusters explains the most, because the steepest decrease in this total within sum of the squares. And then going from 2 to 3 explains some a little bit more, 3 to 4 a little bit more, and so on. You can see that by adding another cluster consecutively, we're always explaining more variability. However, the biggest gains in explaining variability come from the first clusters. So for this case here, I would tell you that looking at this plot, choosing anywhere from 3 to 5 would be reasonable, in my opinion. So 3 to 5 clusters, 3 to 5 zones for this field would be reasonable. Okay, so this is one very popular metric that people use for k-means. But now I want to show you a different one. That is called the I don't even know how to pronounce this. Can someone help me? Silhouette? Is that how you would pronounce it? Okay.
Silhouette, yeah.
Yeah, so the silhouette method is another popular metric to judge how many Ks you need. So I just wanted to ask you to come here and just copy this code. We're going to come below here and paste it. And we're really just going to change the method. So the method here is going to is called S for silhouette. So if we just run this, it should be faster. So I wanna give you some background on what is happening here. So the silhouette method is basically, again, doing k-means from 1 to 10 and using the results to evaluate the silhouette width at each one of those cases. So what happens here is the greater the silhouette width is, it means that the clusters are compact and the observations belong to that cluster. What happens is, for example, if you have one cluster, it is a very variable cluster. You have observations that are very distinct, meaning that they don't belong together. So that's why it's such a low value of average silhouette. So here we want to choose the number of K that has the maximum silhouette width, because it means that clusters are compact and the observations belong to those clusters. This is, and this is on this plot, it's already showing us what is the recommendation. So if we use the silhouette method, it would recommend 2 clusters. Okay, and just let's just take a moment here to realize this metric is subjective, but I would say 3 to 5 is good. The silhouette one is telling 2. So it's telling a different answer than what the first one is doing. So how do you even decide now? Just want to take another step back and say, so when we have complex data, and by complex, I mean just like more than 5 columns that we're using to do clustering, we have to use some metrics like this to give us an answer on K. We cannot, it's not easily accessible just by plotting like we did in those beginning examples. So we have to use metrics to tell us what's the best number of K. Here, these 2 metrics are not giving the same answer. So what? How do we handle that? So I feel like if you are doing research and you're publishing this, as long as you have at least one metric and you're following some objective way of defending your number of K, that should probably be good enough with reviewers. If you are applying this commercially, you know, it's really more of on the application side. So then it really depends. Like if one tells you to have 10 and the other tells you to have 2, maybe it's better to run both, bring in yield data and see, you know, how yield is changing really from zone to zone, and then make a decision that way, a more like applied way of thinking about this problem. Anyways, let's just keep going here. What I want to show you is there is a function here, and please do not run the next chunk yet. Hold on, and I'll tell you why in a moment here. So there is this function called nbclust that, so it takes a data set as well. It takes a distance metric. We haven't talked much about distance metrics, but Euclidean is one of the most common ones to use. That's what we're using. We're not going to go in any more detail here. We're telling to use k-means to include all indices and to test clusters from 2 to 6. To test k-means going from 2 clusters to 6 clusters maximum. So this, I'm asking you to not run this piece of this code here because it took on my computer 5 minutes to run. And what this is doing is it's calculating over 20 different indices all at the same time and letting them vote on what is the best number of K. So that is really, this would probably be the most robust way of doing this, because you're not using 1 or 2 metrics, you're using over 20 metrics. And you're using the vote of the majority to decide what best number of K you should have. So so don't run this because it's gonna freeze your RStudio session for 5 minutes or more. I just wanna launch here my complete version because I wanna show you the output of this. So, and you can run this on your own afterwards. I just didn't want you to get stuck here for 5 minutes, just not doing anything. But this is what it does. So it provided me with saying how many indices that it tested propose a given number of clusters. So you can see here that the maximum, so 10 indices proposed K equals 2 as being the optimum. And it was, so I would say for this data set, we have 2 zones by the means that I'm just showing you here, that 10 indices voted on 2. But also 9 other indices voted on 3. So 3 was a very close second place here. So this data set probably could do well with 2 or 3 clusters. That would be reasonable, but any other number of cluster size have very few votes. So 2, 1, 2, 1, 1, as you can see. And then when you run this function here, it gives you the plot of those votes. So basically the same information, but on a bar plot. So showing that number of clusters equal 2 had the most votes, followed by 3, and then the others were a lot lower. I'm just going to close this. And you can run, again, this on your own. Just didn't want you to get stuck here, waiting for that chunk to go through. Okay, any questions? All right, so let's, on the next chunk here, I really want to create the model or the clustering analysis with this informed decision of using 2 clusters, right? So this is basically the same code that we used before. So use the assignment, we say use the k-means function, we give our data all underscore v underscore n. We say centers equals 2. And again, we decided on 2 because of was the majority vote from over 20 metrics. And I want to again just say n starts, starts equals 10. Okay, so we just run that. And this is our output. And again, it's just giving us the center of those 2 clusters for each one of the variables, and also it gives us a vector with the cluster membership that matches the same number of rows of our incoming data set. So we know exactly what observations in our data, what is the membership of cluster for each one of them. Okay, so k-means is done. We have created our zones, but we haven't plotted them yet, or even explored them, how the different variables are impacting them. So that's what I want to do next here. The thing is, we are already at 10:10. And maybe let's take a vote here. Let's do just like the functions that we're looking at and take a vote. So this is being recorded anyways. So if you do have to leave, that's no worry at all. We can catch up later. I just want to say that the entire next week, we're going to have Dr. Simmerjit Virk talking with you guys about zone creation, really, and variable rate application. I don't think he's going to walk you through an exercise, but he's going to be talking more about the principles, which is going to be super cool. And I think that finishing this exercise today would be cool. However, it's going to take some more time. Maybe we can end up like the next 3 chunks, which may take 5-8 minutes to go through. If you have to leave, that's totally fine. I don't want you to feel like you have to stay. But would you guys prefer to at least go through these chunks here so we can make the map and see how variables are impacting clusters and go, another 5 to 8 minutes extra time today? Or do you just want to stop and catch up in 2 weeks? Any thoughts? Anything? I'm good with whatever. It's really up to your availability, I guess. Does anyone have to leave? And can I stay for 5-8 minutes?
We can go ahead and knock it out.
Okay, go ahead.
I have a Zoom meeting at 10:15.
Oh yeah, absolutely. It's going to be recorded and it's not going to be that much longer. So if you just want to catch up later, I think it's going to be a nice stopping point before you guys see the next week's. Also, let me know if you have any issues. Okay. All right. We kept, okay, I think we lost Tyson as well. That's fine. It's going to be recorded. Okay, let's just keep going here for these 3 chunks and then we can stop there. All right, so what I want to do next is just bring together our incoming data set and append that cluster column on it so we can actually plot that variable in our ggplot. So to do that, we're going to start here on this chunk with our incoming data set. So that's the all underscore v underscore n. Add a pipe here. And what I want to do is use a mutate function. I want to call this column as cluster, like that. And what we're going to do basically is this object here, this mod KM2, I just want to print so you can see it. So if we just paste that here and use $sign to go inside of this object, it has a cluster column that if we print that, it gives us the vector with the cluster membership. So I basically want to use this and bring this information into our data set and save that into a column called cluster. Also, I want to add a pipe and another mutate here. I want to, so this, when we just do this, if I just print at this point and print zone df, it is an integer. So it is seeing cluster as 1 and 2 as a number. And I actually want that to be seen as a categorical variable or as a factor variable. So to do that, we're basically going to say cluster equals factor and then cluster again. So this way we are transforming cluster into a factor or categorical variable and just overriding on the same column name of cluster. So if we run that, we see now the cluster is being interpreted as a factor, which is what I wanted. And then also something that we're missing here, if you notice, we don't have the geometry, right? This is just a tibble or a data frame. It's not a SF object. So I want to bring back the geometry that we had so we can actually plot this in space. So add a pipe at the end, hit return. We're going to use the function called bind_cols. So this is basically going to bring a column and bind it in our data set. And so now, just to tell you, the bind_cols function is the tidyverse version of the cbind function. They do the same thing really, but I guess I myself use bind_cols just to be more within the the functions used within tidyverse, but they basically do the same thing. I think bind_cols may be more efficient, perhaps. I'm not sure. I think behind the scenes there's some differences that when we're using, we don't see them, perhaps in efficiency of runtime.
Okay.
So I just wanted to tell that. Okay, so what we're going to do then is inside bind_cols, I want to do some wrangling as well. So we could just do like bind_cols all_v. So the all_v, if we just print that, is a data set that has all the 4,032 rows and also has the geometry. However, so if we run everything up until this point, we don't have 4,032 rows because at some point when we created all vn, we did the drop in a. So to make sure that all v and all vn and everything after are matching, we have to do a drop in a on all v. So we do that, just we did before. And really, once we do this, the only piece of information that I really want from all v is geometry. So I'm just going to do a select on that. So do a pipe, dplyr, select geometry. So if I just run this for you to see, this is what we're creating. And this is what we are binding this column in our data set. Okay. So if you just run that, oh, and I think something else we have to do as well. So even though now we added the geometry here, but it's still not an SF object. So I just want to make sure that this is seen as an SF object by adding a pipe and doing st_s_sf. So this will make sure that that geometry is actually seen as an SF object. And this is what we get. Okay. All right, let me see here. Yeah. So let's do a cluster map here. The first thing I want to plot all these pixels or all these polygons and have them colored according to that cluster membership so we can see what's going on the field. So we can start with our zone df object, which we just created above, and start with a let's see, yeah, start with a ggplot call. we leave it empty at that higher level of ggplot. At a plus, hit return. We're going to use a geom SF. Yeah. And we're going to use open the astatics function. And what I want to do here is say fill equals cluster. So we have the different clusters having a different fill color. And I also want to come here outside of the AS function and say color equals NA. So we don't see the outline of the pixels. Also, want to add a plus. And I want to add another geom-SF to add the geometry, or sorry, to add the boundary. So we say data equals boundary W. And again, just say fill equals NA so we can see through the boundary. And I also just want to change the color scheme. So add a plus there. Let's do a scale underscore fill because that's what we're changing, underscore colorblind. So this is not the Verides scale. It's a different scale, but it is also colorblind. So if you just run it, these are our clusters, right? So this is how this is how k-means took in elevation, slope, aspect, hill shade, EC30, EC90, and combined those into two groups. These are our spatial groups. So this right here could be, the step where you would export this into a shapefile or perhaps some format that could be imported into a precision ag equipment that has software that could use that information and really change some inputs, right? Where we have these zones. Of course, we are not making any recommendations at this point. So maybe this is not as useful yet because we haven't really used this information to change anything in space. But this is just so we can visually assess how our clusters were created and how they're working out for this field. So right now at this point, we don't know really like how the variables that we gave k-means are changing between the two clusters, so that we don't know that yet. And we also don't know if these clusters are even related to yield, because if you notice, we did not give yield information to the clustering algorithm. So these could actually be complete, not likely, but it's possible that they could be totally decoupled from yield. Like maybe they have nothing to do with yield. It's just the way that the variables that we gave them are changing. And that this is something interesting to think about in precision ag is what variables do you use to create your zones. So normally, what I think it's common is for you to create variables that impact yield, and then use yield to validate. So not use yield directly on the clustering side, but just at the end, you bring yield and validate and see how yield is changing for different zones. Because that would be something, a way to make sure that your zones are actually meaning something as far as yield potential, yield environments within your field. Okay, I had another piece of code here, but I think we can skip that for today because it's going to get a little bit more complicated. And I want to have more people being able to be live as well in case they run into issues. So we can stop here, and the next steps that we'll do probably like a week from today is going to be to validate the clusters and then export these clusters to file so we can use it later. And just so you know, following up when we finish this exercise, the next steps then will be to use these clusters to create a variable rate input application recommendation, and then do a profitability map based off of the clusters and the variable rate that we use that were based on the clusters as well.